Welcome to my channel. This is GeoMethod, where we turn tricky geometry into clear, simple steps. Here is today's challenge. Can you find the length x? Take a moment to look at the figure and see if you can spot the idea. Then stay with me, and we will build the full solution together, one move at a time. Welcome back. First, look only at the original figure, a right triangle ABC with rays AE and AD splitting angle A into three equal alpha angles. On the base, segment BE is 1, segment ED is x, and segment DC is 3. We want x. The direct solution measures every ray from the leg AB. Ray AE is alpha away from AB, ray AD is 2 alpha away, and side AC is 3 alpha away. This is why cosine will enter the first solution. Because ray AE splits angle BAD into 2 equal alpha angles, it is an angle bisector in triangle ABD. The angle bisector theorem gives BE over ED equals AB over AD. Now substitute the given base lengths. Segment BE is 1 and segment ED is x, so the left side becomes 1 over x. In right triangle ABD, the angle at A is 2 alpha. Segment AB is adjacent to that angle, and AD is the hypotenuse. Therefore, AB over AD is cosine of 2 alpha. Chaining the two facts gives our first master equation. Cosine of 2 alpha equals 1 over x. Now use the second bisector. Ray AD splits angle EAC into 2 equal alpha angles. So in triangle AEC, the theorem gives ED over DC equals AE over AC. Substitute ED equals x and DC equals 3. Now x over 3 equals AE over AC. Both AE and AC are hypotenuses of right triangles sharing the same leg AB. So AE is AB divided by cosine alpha, and AC is AB divided by cosine 3 alpha. When we divide, AB cancels, leaving cosine 3 alpha over cosine alpha. Here, the direct route asks for the triple angle identity. It says cosine 3 alpha is 4 cosine cubed alpha minus 3 cosine alpha. After dividing by cosine alpha, the ratio is 4 cosine squared alpha minus 3. Therefore, the second master equation is x over 3 equals 4 cosine squared alpha minus 3. Let C be cosine squared alpha. Since cosine 2 alpha equals 2c minus 1, the first equation gives 1 over x equals 2c minus 1, so c equals x plus 1 over 2x. Substitute that value of c into equation 2. The right side becomes 4 times x plus 1 over 2x minus 3. Simplifying gives x over 3 equals 2 minus x over x. Cross multiply, move everything to one side, and the quadratic is x squared plus 3x minus 6 equals 0. The quadratic formula gives negative 3 plus or minus square root of 33 over 2. Since x is a length, we keep the positive root. Negative 3 plus square root of 33 all over 2. The direct route works, but it imports a serious formula. Let us change the mission. We will solve the problem using only geometry, and then ask something stronger. Can the diagram itself explain where the triple angle formula comes from? Here is the auxiliary line, aha! Reflect triangle ABE across segment AB. The copied point is F, and triangle ABF is congruent to triangle ABE. The copy gives AF equals AE. Call that shared length A. It also gives BF equals BE, so BF is 1. Now look along the straight line FBEDC. Segment FE is 1 plus 1, so it is 2. Segment EC is x plus 3. Finally, call AC by the name B. Now, stop. Look at what the reflection created. Above ray AE, two alpha angles combine to make 2 alpha. Below it, the other 2 alpha angles also make 2 alpha. Wait, those 2 large angles match exactly. So AE is not merely another line. It is the angle bisector of angle FAC. There it is. The copied triangle has manufactured the theorem we needed. Apply the angle bisector theorem in triangle AFC. Since ray AE is the bisector, FE over EC equals AF over AC, which is A over B. Substitute the new split. FE is 2, EC is x plus 3, AF is A, and AC is B. So 2 over x plus 3 equals A over B. The original ray AD is still a bisector in triangle AEC. It gives ED over DC equals AE over AC. So x over 3 equals A over B. And now the hidden ratio snaps into place. Both equations equal the very same quantity, A over B. So their left sides must equal each other. 2 over x plus 3 equals x over 3. That single match is the whole trick. Cross-multiplying gives x times x plus 3 equals 6, which is the same quadratic as before. Again, the positive root is negative 3 plus square root of 33 over 2. Now comes the second aha. Start this part from scratch. Ignore the special labels 1, x, and 3, and keep only the 4 alpha angles created by the reflection. If we name the base pieces M, N, and P, the same picture actually explains why the cosine of 3 alpha formula is true. Forget the special numbers for a moment. Let BE be M, ED be N, and DC be P. In the reflected picture, the apex now shows 4 consecutive alpha angles. The first bisector, ray AE, in triangle ABD, gives M over N equals AB over AD. But that side ratio is cosine 2 alpha, so M over N equals cosine 2 alpha. The reflected copy argument gives the same auxiliary relation, but now symbolically. FE is 2m, EC is n plus p, and the other bisector ratio is n over p. So 2m over n plus p equals n over p. Rearrange that base equation. Cross-multiply to get 2mp equals n times n plus p. Divide by np, and it becomes 2m over n equals 1 plus n over p. Therefore, n over p equals 2m over n minus 1. The second bisector says n over p equals AE over AC. And the shared leg right triangles say AE over AC is cosine 3 alpha over cosine alpha. Now replace the two base ratios. Since n over p is cosine 3 alpha over cosine alpha, and m over n is cosine 2 alpha, the geometry gives cosine 3 alpha over cosine alpha equals 2 cosine 2 alpha minus 1. Now use the ancient chord viewpoint exactly where it belongs. Hipparchus made the first known chord table, and Ptolemy's surviving Almagest systematized chord calculations. The theorem bearing Ptolemy's name was an engine for combining chords. For central angle 2 alpha, the half chord AM is r sine alpha, while the whole chord AB is 2r sine alpha. Here r is 1, so AM is sine alpha and AB is 2 sine alpha. The cosine rule describes that same whole chord by AB squared equals 2 minus 2 cosine 2 alpha. Equating the two descriptions gives cosine 2 alpha equals 1 minus 2 sine squared alpha. Hence, 2 cosine squared alpha minus 1. Much later, Pitiscus recorded explicit double angle and triple angle formulas in Renaissance trigonometry. The idea itself grew from this older chord tradition. And now, the final reveal. The reflected triangle gave cosine 3 alpha over cosine alpha equals 2 cosine 2 alpha minus 1. The unit circle chord gave cosine 2 alpha equals 2 cosine squared alpha minus 1. Put the two pictures together. One substitution, one multiplication by cosine alpha. And there it is. Cosine 3 alpha equals 4 cosine cubed alpha minus 3 cosine alpha. The formula we had to borrow at the beginning was hiding inside the geometry all along. So remember the two reveals. First, reflection manufactures an angle bisector and solves x using pure geometry. Second, the reflected construction and the unit circle chord explain the double angle and triple angle formulas themselves. The answer is -3 plus square root of 33 all over 2. But the deeper result is that the formulas are geometry in compressed form. And there we have it, clean and verified. If you like this video, do me a quick favor and tap the like button, then subscribe to GeoMethod so the next puzzle lands right in your feed. Have a slicker approach? Drop it in the comments. I read every one. Thanks for solving with me, and I will see you in the next one.